Okay, this green curve is a graph of the function f of x equals a times b to the x plus d. Now in this case we have a set to 1, controlled by the slider. We have b set to 2, controlled by this slider, and we have d set to 0, controlled by this slider. Now we've seen this function before. It has an asymptote of y is equal to 0, so it approaches that but never reaches it. It has a y-intercept of 0, 1, because 2 to the x, when x is 0, is equal to 1. And we know it has limits as x approaches positive infinity, f of x approaches infinity. As x approaches negative infinity, f of x approaches 0. Now we've seen what happens when we change the value of a. We certainly see that the y-intercept is going to change. We see that the asymptote, however, does not change. And we see what happens that when we change a to the limits, which is that they also do not change. But what happens now when you add a constant value to the function? Let's see what happens. So with d now set at 0, we can see what the function looks like when graphed. But what happens as d becomes greater than 0? Let's say in this case we'll set it equal to 1. Well, clearly the graph of the function just slid upwards. We carried out a translation of the curve in a positive direction of 1 along the y-axis. Now notice our asymptote has changed from y equals 0 to y equals 1. Our y-intercept, not surprisingly, went from 0, 1 to 0, 2. And our limits, as f of x approaches, as x approaches positive infinity, f of x still approaches infinity, but as x approaches negative infinity, f of x approaches negative 1, again, never quite reaching it. As we change the value of a, just what we would think would happen. When a is negative, our curve is below the asymptote. When it's positive, our curve is above the asymptote. Notice that in this case, when we have both a and b positive, that the value of our function is increasing. So we know that as x gets larger, f of x also gets larger. On the other hand, when we change b to have a value between 0 and 1, now we have a decreasing curve. When x is lower, f of x has a higher value. So it's now decreasing. Notice that as I change b, though, the y-intercept and the asymptote and the limits do not change. When I now make a negative, when b is between 0 and 1, now we have that the function is increasing because it starts with a f of x having a negative value and then approaching the asymptote from the negative side but never quite reaching it. So now we have an increasing function. But again, changing the value of a does not change the asymptote. It does change the y-intercept, but it does not change the limits. So what you'll be thinking about is, how can I use these properties to create a function that will describe what happens to the temperature of a body, a human body, when it dies. And in particular, when it dies, the temperature of that body will start to approach room temperature. And it will approach it exponentially. That is to say, the difference between the temperature and the room temperature will decrease exponentially. Your next task will be to model that for a particular situation. So now you can see that we've changed the window setting so that the y-axis now goes up to over 100, and the x-axis has stayed approximately the same. Now we've plotted 2 points from your CSINewton handout, and we can see that there's a slight decline in temperature from 4 a.m. to 5 a.m. Your job is to find the curve that fits these 2 points and then use that curve to make a prediction about the temperature of the body. you'll see that you'll be needing to make some adjustments to the value of A, which will have to be increased by some unknown quantity. B will certainly have to change from a value greater than 1 to a value between 0 and 1. And D will have to change. And you'll have to make changes to all three of those in such a way as to make the curve fit the points. And again, make a prediction about when this, well, actually it's an estimation about when this temperature was equal to 98.6 degrees.